In this video, we're going to take a look at solving trig equations in radians. Now, the good news for this video is we are not introducing any new material here, because this is largely a recap of first year material for solving trig equations. The only difference here is then, rather than giving the solutions in degrees and working with these trig equations in degrees, we're now working in radians. So the method and the working is almost identical. So there's two main approaches really here to solving these trig equations. The first method is a graphical approach, and the second method is what I prefer, and that is a cast diagram. So I'm going to stick to method 2 throughout this video and similar videos where we are solving trig equations. However, if you do prefer method 1, so using a graphical approach, that's absolutely fine. So you can stick to that as well. It's completely up to you, and it's just a preference thing. So let's just quickly recap then a cast diagram here. Now for a cast diagram, what we do here is we have our 4 quadrants. So let me just quickly draw these 4 quadrants in here. We'll get something that looks, say, like this here. So this quadrant here is for C, so that's for cosine. This quadrant here is for A, so this is for all trigonometric functions. This quadrant here is for sine. And then finally, this quadrant here is for tangent, so tan. Okay. So what this tells us then is where each trigonometric function is positive. So in this quadrant here, all trigonometric functions are positive. In this quadrant here, only sine is positive. In this quadrant here, only tan is positive. And then finally, for the very last quadrant here, only cosine is positive. Now, the way that this works then is we go on to solve our trig equation. So we do x equals, so it'll either be sine inverse, cos inverse, or tan inverse. That depends obviously on which trigonometric function we are working with. And what we get then is a solution. Okay. So the initial solution that we get there would be this angle here, okay, for A. So this is for all trigonometric functions. So I get my angle here, okay. Now, let's say that is pi over 4. Okay, so that's pi over 4 there. So we have pi over 4 there. Now, let's say we're working with sine here, okay. So sine is obviously positive in this quadrant here because all trigonometric functions are positive in this quadrant. Now, the next solution then would be in this quadrant here. So this is for S, for sine. So we have another angle here in this quadrant. So we've got this angle here. Now, this angle here will be the exact same. So that will also be pi over 4. But clearly that isn't the next solution here. Okay. So the way that this works then for a cast diagram, let me do this in a different color just to highlight this. The way that this works is we go from what would be the x-axis here, this line, and we go around until we touch these lines. So from here to this line here, like so, clearly that would just be this angle here. So that would just be pi over 4 anyway. Okay, should hopefully be quite clear and obvious. Now for this angle here, so we're going from this line again, all the way around. So if I go through that solution there, like so, until we touch this line here, okay? And what we're looking for is the angle that's formed from this line here, going round until we meet this line here, okay? So clearly it won't be the pi over 4 again. That was this initial solution here. So how would we deduce this angle that's formed here, going from here all the way around until we meet this line here? Well, the way that this works then, if we think about this in basic properties of angles, clearly this would just be pi, because we are working in radians now. So pi radians minus this angle here. Okay, so it's going to be pi minus pi over 4, this angle here. So pi minus pi over 4. So here I want to keep this in exact form. So if I've got pi minus pi over 4, well, what I need here is a common denominator. So this would be 4 pi over 4. So 4 pi over 4 minus pi over 4. And that would give me 3 pi over 4 there. Okay, so my next solution then would be 3 pi over 4. And we'd keep going here. Now, obviously, it depends on which trigonometric function you're working with and the periodicity. So let's just quickly recap the periodicity of each trigonometric function as well. So go back to my original pen color. So for sine and cosine, so make a note of this here. So sine and cosine they have a period. It just means they repeat every 2 pi radians. Okay, so they have a period of 2 pi radians. So you should be aware that they repeat every 360 degrees. So obviously we are working in radians now, so they have a period of 2 pi radians. So what about tan then? Well, tan has a period of pi radians. It repeats every 180 degrees. But again, we don't want to think in degrees now, we want to think in radians where we can. So tan has a period. So tan has a period of pi radians. Okay. And clear then, the next set of solutions, if I need any further, obviously it depends on the domain for the variable that we're looking to solve for. Obviously we need to take into account the periodicity of the three functions. Okay. But we'll see that in more detail as we work through these questions. Okay. So that's a very, very brief introduction here into solving these trig equations. But do watch the first year material, first year video on solving trig equations, just if you need a recap. Like I said, this is largely just a recap of that material anyway. But now obviously just looking to solve these while we're working in radians. So that's everything that we need here really for our introduction. So what we're going to do now is just take a look at a few practice questions here for solving trig equations in radians. Starting off with question 1 then, where we have a nice easy trigonometric equation to begin with. So question 1 says solve for x being between 0 and 2 pi, 2 sine x equals 1. So to begin with here, let me just write down the original trigonometric equation. So we have 2 sine x equals 1. So 2 sine x equals 1. Now the first thing that we need to do here is isolate sine x. So I need to go to this 2 here in front. So we're timesing sine x by 2. So the opposite of timesing by 2 is to divide by 2. Okay, so we're going to divide both sides by 2 here. So if we do that, we get left with sine x equals a half. So sine x equals a half then. Like so. And what we've done here then is we've isolated sine x. And that's perfect. That's what we're looking for here. Once we isolate sine x, we now take sine inverse of both sides. That would leave us with x. So on the left-hand side then, once we take sine inverse of sine x, we get x. So therefore, x is equal then to sine inverse. So sine inverse of a half then. So sine inverse of my right-hand side here, which is a half. Like so. Now, obviously, we are working in radians here. That's the whole point of this video. Obviously, we know that from the domain here. So x is between 0 and 2 pi. So just to ensure that your calculator is in radians mode rather than degrees mode, it's a really easy mistake to make, especially in an exam. Okay. So if your calculator is in the correct mode, so we're in radians mode here, put this into your calculator. And what you should find then is for x here, we get pi over 6. So x is equal to pi over 6 then. Now, we're not done here. We need to consider the full set of solutions here. So we're between 0 and 2 pi. What we've got here is just one solution. Okay. So the remaining solution, we can find that in a number of different ways. We could do a graphical method, for example, or we could also use a cast diagram. And that's the method that I'm going to use for this video here. Okay, and you'll see that in the introduction. So let me just quickly draw my 4 quadrants here just to help illustrate what we're looking for. It doesn't have to be perfect, but let's say this is our cast diagram. So we've got C, A, S, and T. Okay, and this gives us our cast diagram. Okay, so we go counterclockwise here, or anti-clockwise around. Now, this tells us where each trigonometric function is positive. So if we're working with sine here, well, sine is going to be positive in this quadrant here because all trigonometric functions are positive in this quadrant. So we get this angle here. Now this angle here would be the angle that we've just found, pi over 6. That's pi over 6 there. And we're also in this quadrant here where the S is. That represents sine. So we've got this angle here as well, like so. Now, that's my first solution. That's what we've just found here, pi over 6. Now for the second solution here found in this quadrant, it's not this angle here that we're actually looking for. So let me just do this in a different colours to make it clear. Let's do it in, say, blue. What we're actually looking for here then is going from what would be my x-axis here around until we touch the line. So for this angle here, clearly from here to there was just this angle anyway. So it was just pi over 6. Okay. The same is now true going from here all the way around until we touch this line here. We're looking for the angle that's formed. Okay, so from here to here, what's the angle? Well, clearly that would just be, if you think about it in degrees just to begin with, that would be 180 degrees minus this angle here. So for example, if that was, say, 50 degrees, it'd be 180 minus 50. So this angle here would be 130. Okay, should hopefully make sense, just basic properties of angles. So now, if we're working in radians here, well, 180 degrees in radians, that would be pi radians. So in that case then, what I've actually got here, let me just make this clear as well. This angle is the same here as this angle. So this is also pi over 6. So in that case then, my second solution here, my other solution, let me just write this down. So other solution, this is equal then to pi. That's 180 degrees, but think about this in radians rather than trying to think about it in degrees. So it's pi radians minus what we've got here. This angle, like we said, this is pi over 6 minus pi over 6, like so. And what you want to be doing here is working out this difference here in its exact form. So don't use your calculator here. Obviously, it's just basic properties of fractions. So I've got pi minus pi over 6. Well, obviously, we need to get this over a common denominator. So this would be 6 pi over 6. So 6 pi over 6 minus pi over 6. And in that case, then we simply get left with 5 pi over 6. Okay. And there we have it. So we're not going to have any more solutions now within this domain here for x. Any more solutions now would fall outside of this domain here. So therefore, we would omit that solution. Okay, so in that case then, our full set of solutions here for x is x is equal to pi over 6. And x is equal to 5 pi over 6. Okay. And there we have it. So that gives us the solution there to question 1. Moving on to question 2, then we're asked us to solve for x being between 0 and 3 pi, tan x plus 4 equals 5. So again, what we're looking to do here to begin with is isolate the trigonometric function on its own. So what I want to do here is get tan x on its own. So to do that, we need to subtract 4 off both sides. So let's just start by writing down the original trigonometric equation here. So we have tan x plus 4. And that is equal to 5. So from here, what we're going to do then, like I said, is subtract 4 off both sides. So therefore, we get tan x equals 1. So tan x equals 1. And because we now have the trigonometric function isolated here, we can now take tan inverse of both sides. So if we do that here on the left-hand side, we simply get left with x. So you get x on the left-hand side. On the right-hand side here, we get tan inverse of 1. And tan inverse of 1, obviously just ensure that you are working in radians mode here on your calculator. Obviously, if you do recognize the exact trig value here, what we get then in radians is pi over 4. So we get pi over 4 there. Now, the domain here for x is between 0 and 3 pi, so clearly this won't be the only solution here. It's up to you. You can use a graphical approach here or use a cast diagram. Like you know, I do prefer the cast diagram here. If I quickly draw my 4 quadrants here, like so. I've got C, A, S, and T. So in this quadrant here, all trigonometric functions are positive. So this angle here would be my pi over 4. That's pi over 4 there. This is for sine. This T here represents tan. So this would be where tan is positive as well. So we're in this quadrant here. So we've got this angle here. So that will also be pi over 4. But that isn't the next solution. So the next solution is given by the angle, let's do it in blue, that's formed from what would be our x-axis here, all the way around until we meet this line here. Okay, this line here. So how do we deduce the angle that's formed? Well, that would be pi radians here because it's 180 degrees, plus this angle here. So let's just make a note of this then. So my next solution is given. So the next solution is equal to pi plus this angle here. So pi plus pi over 4. So pi, that would be the same as 4 pi over 4 plus pi over 4. And if we evaluate this here, we get 5 pi over 4. Okay. So we get 5 pi over 4 there. Now, again, we're still within this domain here. So we need to keep going until we find a solution that doesn't fall within this domain here. So because we know that tan is periodic about pi, so it repeats every 180 degrees, in that case then, I can just simply add pi now to each solution here. So what I mean by that is, for my next solution then, this would simply be 5 pi over 4 plus pi. Okay, we then do the same for the next solution, so on and so on until we find a solution that doesn't fall within this domain. So my next solution, let's write this down. My next solution, that's given, like we said then, as the previous solution plus pi. So 5 pi over 4 plus pi. So that's the same then as 5 pi over 4 plus 4 pi over 4. So that would give me 9 pi over 4 there, like so. Again, just check that this solution does fall within this domain here, and in this case, we can see that it does. So we keep going here. So for my next solution now, I won't write this out in full, but what I can see then straight away here is if we have 9 pi over 4, and I add pi, so like we do here, we just take the previous solution, add pi to get my next solution. Well, in that case then, I'm going to have 9 pi over 4 plus 4 pi over 4. Let me just do this over here. So 9 pi over 4 plus 4 pi over 4. When I evaluate this here, we get 13 pi over 4. And clearly in this case here, then we now fall outside this domain. So 13 pi over 4 is greater than 3 pi. So therefore, this is the last solution then for this trigonometric equation. Let's just write out all the solutions here then. So therefore for x is equal, so we start with the first solution, pi over 4, pi over 4, 5 pi over 4, and then finally 9 pi over 4. Okay, 9 pi over 4. And there we have it. So that's the solution there to question 2. And finally then, if we take a look now at the very last question here, question 3, where we have a slightly more complicated question. So question 3 asks us to solve for theta being between 0 and pi, 2 cos 4 theta plus 3 equals 4. Now what makes this question here slightly more complicated is the fact that the argument of our trigonometric function here isn't just x or theta. So we do need to change the working ever so slightly here, nothing too complicated, but it does change things, like we said, ever so slightly. Now, the first thing that we need to do here is account for this in terms of the domain. Notice the original domain here is just for theta. We have 4 theta here for the argument. So what I need to do then is change the domain to be accounting for this. So I want the domain to be for 4 theta. So to make that happen, we need to times through by 4 here across this inequality. So 0 times by 4 would still be 0. Theta times by 4 gives me the 4 theta that we require here. We get 4 theta there. And then finally, pi times by 4 gives me 4 pi. Okay. So that's the first thing that we should always do here in a question like this, where the argument isn't just, say, x or theta. Now from here, we're just going to solve this in the regular way. So let me just start by writing down the original trigonometric equation here. We have 2 cos 4 theta. So 2 cos 4 theta plus 3 is equal to 4. Okay. So obviously what we want to do here is isolate for cosine 4 theta. So we need to get rid of the plus 3 here and this 2 in front. So the first thing I'm going to do here is subtract 3 off both sides. That would leave me then with 2 cos 4 theta. So we get 2 cos 4 theta there. The 3 would cancel. Obviously 3 minus 3 is 0. And then on the right hand side we get 4 minus 3, which is 1. Hopefully all nice and straightforward for now. And again, we need to get rid of this 2 here in front. We're looking to isolate cos 4 theta here. So we divide both sides by 2. So that leaves me with cos 4 theta here. And that is equal to 1/2. And because we've isolated cosine here on its own now, we can now take cos inverse of both sides. If I take cos inverse off the left-hand side here, that would just leave me with 4 theta. So therefore, 4 theta is equal to cos inverse of my right-hand side here, which is 1/2. So cos inverse of 1/2. So again, just use your calculator here, just make sure it's in radians mode rather than degrees mode here. If you put this into your calculator, then what you should get for cos inverse of 1/2 is pi over 3. So we get pi over 3 there. Now clearly we have quite a large domain here, so this would not be the full set of solutions here. Okay. So what I'm going to quickly do here is draw out my cast diagram. If I draw out my 4 quadrants here, got C, A, got S, and then finally T here. So clearly this first solution here, this pi over 3, is in this quadrant here because all trigonometric functions are positive in this quadrant here. So this is pi over 3. This is for sine. This is for tan. So we're clearly in this quadrant here. For C, that's for cosine. So I've got this angle here. Now, that's not the angle that we're looking for. That angle there will also be pi over 3. So that's also pi over 3. Okay. But what we're looking for here, let me just do this in a different color just to highlight this. Let's do it in blue. We're looking for the angle that's formed going from what would be our x-axis here all the way around until we meet this line here. Okay, we're looking for this angle that's formed. So how would we find that angle? Well, if we just think about this for a moment, basic properties of angles here. If we start at this point here, so on this line here, and we go all the way around until we touch this line again, this is one full revolution. So in other words, it's 360 degrees. But obviously, we're not working in degrees here. We are working in radians. So 360 degrees, that is 2 pi radians. So in that case then, the angle that's formed would simply be 2 pi radians minus this angle here, which is pi over 3. So let me go back to my original pen color. My next solution then. So my next solution is given as 2 pi minus pi over 3, this angle here. So again, we want to keep this exact where we can, and clearly we can do that here. So obtaining a common denominator here, we get 6 pi over 3 minus pi over 3. And clearly in that case, then we get 5 pi over 3. So we get 5 pi over 3 there. So now we need to keep going here because clearly with our domain here from 0 to 4 pi, we're going to have a couple more solutions at least here. Okay. Now don't forget that cosine here is periodic 2 pi radians, so every 360 degrees, but clearly we want to keep this in terms of radians, so every 2 pi radians. So now we can easily obtain the next solution here. So let me just write this down. So my next solution then. So far what we've got here is pi over 3 and 5 pi over 3. So my next solution then would be given by the original solution here, pi over 3, plus 2 pi radians, because it repeats every 2 pi radians. So in that case then, my next solution, like we said, is pi over 3 plus 2 pi. So clearly, again, we keep this exact then. We've got pi over 3. 2 pi, like we've already seen here, is 6 pi over 3. So plus 6 pi over 3. Simplify this here then, and we get 7 pi over 3. Okay. Now we're still within this domain here. So we're going from 0 to 4 pi. 7 pi over 3 clearly falls within that. So we keep going here until we find one that isn't within the domain. So my next solution then, we keep going. And you might be able to see the pattern that's going to form here. So for my next solution here then, after 7 pi over 3, this would be the next solution along plus 2 pi radians, because it repeats every 2 pi radians. So you can kind of see why this works here then. Like we said, it's 5 pi over 3 plus 2 pi. So 5 pi over 3 plus 2 pi, so that's the same as 5 pi over 3. 2 pi is 6 pi over 3. And if we simplify that, we get 11 pi over 3. Now we are getting pretty close to the 4 pi here, the upper bound here, or the upper limit on my inequality here. So 11 pi over 3. So if we just consider the next solution here and whether this would fall within the domain, well, that's going to be 7 pi over 3 plus 2 pi. So if we just quickly do it over here, 7 pi over 3 plus 2 pi, that's the same as 7 pi over 3 plus 6 pi over 3. That would give me 13 pi over 3. And clearly that is greater than 4 pi. Okay, so in that case, then we omit this solution here, so we wouldn't include this. So therefore, what we found here is the full set of solutions for 4 theta. So from here then, we can see that 4 theta is equal to, so we've got pi over 3. We then have 5 pi over 3. 7 pi over 3. And then lastly, 11 pi over 3. Okay. Now we are just looking for theta here. That's what we're looking to solve for. This is for 4 theta. So clearly we can obtain these solutions for theta by just dividing through by 4. So in that case then, theta is equal to, well, if we divide through by 4 here, so dividing through by 4, if I've got pi over 3 and I divide that by 4, that's just the same as timesing by a quarter. So pi over 3 times by a quarter, so that's the same as pi over 3 times by 1 over 4, I get pi over 12. And hopefully you can see here then for each solution now for theta, I'm going to take the respective solution here and just times the denominator by 4. So I'm going to get 5 pi over 12. I get 5 pi over 12, 7 pi over 12. And then finally 11 pi over 12 there. Okay. And there we have it. So that's the full set of solutions there for theta. And that gives us the solution there to the very last question, question 3. And that brings the end of this video on solving trigonometric equations in radians.